Hi, this is Alex from devstories.eu. Scikit-image, the AI image pipeline, episode 3 of 5. Neural networks are brilliant at finding patterns, but they will happily memorize the specific lighting of a room instead of the object you want them to detect. To fix this, we need to standardize the variance in our datasets through contrast, exposure, and AI robustness. Consider a dataset of medical x-rays collected from a dozen different hospitals. The scans come from different machines with wildly varying calibrations. Some images are dark and muddy, while others are washed out and bright. If you feed this raw data into a neural network, it will likely overfit to the lighting conditions of specific scanners, rather than learning to identify the underlying pathology. You have to normalize the exposure before training begins. The first step in this standardization is often removing irrelevant information. If the structure is all that matters, color is a distraction. You can use a function called RGB to gray to convert colored images into single-channel grayscale arrays. This reduces the dimensionality of your data and forces the model to evaluate pure luminance. Once you are working strictly with luminance, you need to align the baseline brightness across your dataset. This is where rescale intensity comes in. This function performs a linear stretch on your image data. It takes the darkest pixel and maps it to the lowest possible value, like 0, and maps the brightest pixel to the highest possible value, like 255. Every pixel in between is scaled linearly. Here is the key insight. A simple minimum to maximum stretch is fragile. A single dead black pixel or a bright artifact from a piece of dust on the sensor will dictate the entire scale. The stretch will compress your actual anatomical data into a narrow, useless band of grays just to accommodate that one extreme outlier. To solve this, you use percentile clipping. Instead of stretching from the absolute minimum and maximum, you calculate the 2nd and 98th percentiles of the pixel values in your image. You then pass those percentiles into the rescale intensity function as your input range. The function will chop off the extreme 2% of bright and dark pixels, setting them to pure white and pure black, and linearly stretch the remaining 96% of the data. This guarantees that the bulk of your structural data uses the full dynamic range, completely ignoring random artifacts. Sometimes a linear stretch is not enough. You might have an X-ray where the data is captured, but all the pixels are clustered around a few specific shades of gray, making the image look flat and obscuring details. For this, you use equalize hist, which stands for histogram equalization. Histogram equalization is a non-linear process. Instead of just stretching the boundaries, it analyzes the frequency of every pixel value in the image. It then spreads out the most frequent intensity values across the entire available spectrum. If a large portion of your X-ray is trapped in a narrow band of dark grays, histogram equalization will pull those grays apart, assigning them new values that span from black to white. This artificially boosts the local contrast, revealing subtle textures and boundaries that were previously hidden in the muddy areas of the scan. Standardizing your dataset with these techniques ensures your model evaluates the actual shape and texture of the subject. A robust pipeline removes the irrelevant variance of hardware calibration, forcing the neural network to learn the signal rather than the noise. Thanks for spending a few minutes with me. Until next time, take it easy.